In this video, we're going to be talking about Gauss's law. And I know you're thinking,
law school's for people who are boring and ugly and serious.
Sorry, sir, but we got to have some law.
So let's get into it. Roll the intro.
Do you feel the vibes?
So despite being named after Carl Friedrich Gauss, Gauss's law was first discovered and formulated by Joseph Louis Lagrange in 1773. But it was popularized by Gauss in 1835, so naturally Gauss got it named after him.
Scotty, I can't change the laws of physics.
Gauss's law is a divergence law, which means that it has to do with the divergence of a vector field. If you haven't taken Calc 3 yet, you might be like,
No! God, please, no! No! No!
That stupid law. This isn't fair.
But don't worry, because we'll primarily be using the integral form. The integral form is simply that the flux from the object is equal to the charge enclosed by that object divided by the electric permittivity, or epsilon naught. This allows us to figure out an electric field for certain geometries of charge by creating a surface of easily distinguishable charge that goes through that point, and then evaluating the enclosed charge for that surface. Now, when you look at this equation, you might think,
No, that's a bit of a problem.
but it's pretty simple. The circle surrounding the integration just means that this is a closed surface, or that this is the surface area of a three-dimensional object that is completely closed. If you don't have a closed object, you cannot have an enclosed charge. Ergo, this makes perfect sense.
Possession is 9/10 of the law.
Alright, I think an example at this point would be prudent. This will help illustrate how much easier it is to solve a Gauss's law problem for the geometries that it's capable of doing than dealing with continuous charge.
To flout the law.
So let's look at our example from continuous charge. Now, Gauss's law requires certain symmetries, so in this case we're going to have an infinite line of charge, rather than simply a finite length. This would also apply if your distance between the point that you're trying to analyze and the line of charge is significantly smaller than the length of the line of charge. Alright, so similar to our last problem, we're going to have a line of charge at a point P that we want to know the E field at. That is a distance Z above the charge. The total charge on the line will be Q, and the length in this case is infinite. We're going to make a very similar symmetry argument that we made before. If it isn't painfully obvious to you by now that you need to have gone and watched the continuous charge distribution video.
Watch it.
Okay, you watched it? Really? Okay, good. Alright, then following the same logic as before, we're going to say that the E field should only be pointing outward from the charge distribution, since all the components in the direction of the charge distribution should cancel. Then we're going to apply Gauss's law.
You know the law.
In order to do this, we create a Gaussian surface. That Gaussian surface should simply just be something that has a constant E field. In this case, I'm going to use a cylinder. That's because the two end caps should have a flux of 0, since the area vector points perpendicular to the E field. And the cylinder is radially symmetric about the continuous distribution of charge. So the E field will be the same for every radius distance that the charge is from a specific point. So in this case, my cylinder will have a radius of Z, and that means that I can find the E field at point P. Since my E field will be constant over the surface area at radius Z for the cylinder due to its symmetry, my integration for the flux breaks down, and I simply get the E field times the surface area of that cylinder. And that's one part of Gauss's law down. The next part just involves finding the charge enclosed by that cylinder. We're going to section off the part of the line of charge that exists within the cylinder, and assume that it has the same linear charge density as the rest of the line. That means that the linear charge density will also be equal to the charge enclosed by the cylinder divided by the length of the cylinder. So the charge enclosed is simply the linear charge density times the length of the cylinder. Now we can take the integral form of Gauss's law, which is that the flux from the E field is equal to Q enclosed over epsilon naught. All we have to do is replace the flux with E 2 pi Z L and Q enclosed with lambda L. Then we solve for E. This gives us the E field at any radius Z, which is where point P happens to be. Now let's compare what we got in the continuous charge distribution to what we got here. At first glance, you might think these don't look anything alike. But if we recognize a couple of things, we can see something pretty immediately. The first is that for an infinite charge distribution, L is much greater than Z, so we need to take that limit. Then, K is equal to 1 over 4 pi epsilon naught. This is the definition for Coulomb constant. And finally, the linear charge density is equal to Q over L. Making these substitutions, we can see that we got the exact same answer through charge distribution as we did through Gauss's law. But Gauss's law is significantly easier when we pick the right shape. But how can we ensure that we've picked the right shape? Well, in order to make the math easy, we want a shape that has some form of symmetry about our charges. For example, in my example problem, it was radially symmetric. This should also allow you to easily calculate the charge enclosed. Then, our E field needs to be easily represented over each section of the area as either 0, a constant, or an easy-to-integrate function. We really prefer to avoid the easy-to-integrate function and much prefer a constant or 0. So in my example, I used a cylinder, which was constant over the radial symmetry and 0 on the end caps. And lastly, the area of the shape must be easy to calculate or be well known. In my example, I used a cylinder. If you've passed geometry, you should know how to calculate the surface area for a cylinder. And that's about all you need to know in order to pick a good shape for your Gauss's law problem. And that's the last thing to cover in this video about Gauss's law.
You will obey!
Thanks for sticking with us through our electrostatic series. This unit probably involves significantly more calculus than you are used to, but fortunately the next unit will be on electric potential, which is a bit easier. Don't forget to like, comment, subscribe, and then leave any comments you have in the comment section below. Appreciate it.